Hi there, I'm Steve Cunnington. I'm a postdoc from the University of Manchester, and today I'd like to present to you some exciting results of a cosmological detection using the H1 intensity mapping technique with the MeerKAT telescope, which is a pathfinder to the Square Kilometre Array Observatory. So this is work done in collaboration with all of these people here. And it's work that is now submitted on the archive, which was a couple of weeks ago. So I'm putting the archive number in the bottom of all the slides here. So I encourage people to go check out that paper for more details of these results. Okay, so first of all, the H1 intensity mapping technique, the main aim of this is to try and probe large-scale structure, particularly in our late universe. The reason this is an interesting thing to do is because if you probe the fluctuations from the background density field, there's a lot of information within those fluctuations that tells you things about the nature of gravity, the nature of dark energy, the content of the universe itself. So it's got a lot of useful information. This is something we do a similar technique when we probe the cosmic microwave background, which is probing temperature fluctuations in that. And that so far has delivered the best constraints we have so far on our particular cosmological model. The problem with the CMB is that whilst it's delivered excellent constraints so far, it's fundamentally only a sort of 2D slice of structure that we're probing. So it's close to saturating all the information that's within it. If we go to probing the large-scale cosmic structure, we can probe this in 3 dimensions. And if we do this sufficiently precisely, then we should be able to surpass the constraints that we have with the CMB. So that's the idea behind doing this. So how do we do this? Well, typically, and for the last couple of decades, we've done this with optical galaxy surveys. So this works by, if you have a spectroscopic instrument, you can get a good redshift for the galaxies you detect and record their angular positions on the sky, and you therefore build up a 3-dimensional map of galaxy positions. And on all of these positions, you can do things like 2-point clustering statistics on this field. And by doing that, you're indirectly probing the underlying matter density, because these galaxies are a biased tracer of that underlying field. So this is how you extract the information from within it. So this works very well. The only problem, if we want to go to very large volumes, which we do want to do to be able to surpass the information from the CMB, then doing this with galaxy surveys becomes very time-consuming and expensive, because you need to have in order to sample these volumes very well, you need to have an enormous number of galaxies detected. So instead, the alternative approach is, rather than resolving individual galaxies, which, as I've explained, is very hard to do, we instead just record the combined and unresolved emission from all sources. And the most, this is what we refer to as intensity mapping. The most conventional form of intensity mapping that I guess most people will have heard of will be 21 centimeter intensity mapping, or H1 neutral hydrogen intensity mapping. So what this is doing, it's neutral hydrogen is obviously the most abundant element in the universe, and it will spontaneously emit this 21 centimeter signature, which our radio telescopes can detect. And by just recording the diffuse unresolved emission of this, we can build up this intensity map of neutral hydrogen. And the idea is that you no longer care about detecting individual galaxies. So take this blob here, you no longer care whether that's come from 10, 20, 30 galaxies. You just care that there's that a lot of emission has come from there, so you therefore infer there's a lot of structure behind that blob. So you can do your 2-point clustering statistics on this pixelized field, and in that way you're still indirectly probing the underlying matter density, because this hydrogen will be a biased tracer of the underlying matter as well. Okay, so there's a number of instruments that are going to be aiming to do this and are doing this now as we speak. The one that's probably most people have heard of is the Square Kilometre Array Observatory. This has recently been rebranded as the SKAO, so it's SKA Observatory now, but it's still the same thing. So this comes in 2 parts. There's a component in Australia, which will mainly be focusing on lower frequencies, so higher redshifts. But for late universe large-scale structure, we're more interested in the SKA mid, which is probing these kinds of frequency ranges, which therefore means we're sensitive to these redshifts here. So this will be a huge array, about 200 dishes when it's finally constructed. And this will be doing a whole host of science goals, and amongst them will be doing large-scale structure cosmology using this intensity mapping technique. So its final construction won't be till probably the end of the decade, but fortunately with the SK, it's we're lucky it does this phased rollout where there's lots of other things that we can do beforehand. So there's already Pathfinder telescopes built to sort of guide its design process. And one of these telescopes is the MeerKAT telescope, which I'm showing here. So this is kind of like a mini SKA. So it'd be 64 dishes, final SKA will be 200. And it'll actually go on to be a part of the SKA itself. So it's already built and it's on the same site as the SKA, where the SKA will be built in the Karoo Desert in South Africa. It has these two bands of observations, these frequency bands. It means we're sensitive to these redshifts here. So the current observations we have and the ones we've made this detection in are in the L band, these redshift ranges here. But we're also excited about doing higher redshift observations in the UHF band. The current observations, they're a couple of hundred square degrees that we have at the minute, but ultimately the plan is over the next year or two to start scaling these up and eventually do many thousands of square degrees of surveys across these redshift ranges as well. So already it's going to be delivering huge volumes. So MeerKAT, it's not really just a pathfinder to the SK, it will really be doing state-of-the-art science in its own right. Okay, so just an important point to make because it's very relevant to the results of this paper. It's something many of you will have noticed already. These telescopes, MeerKAT and the SK, they're obviously multi-dish arrays, so they're therefore primarily going to be used as interferometers. The reason you do this is because if you have an interferometer, you effectively then make one giant telescope, which is capable of delivering very good resolution. The best example to demonstrate this is the recent results from the Event Horizon telescope, where they linked up all these different radio dishes, literally on global scales, in order to achieve the exquisite resolution to resolve a black hole many light years away. So this is the idea behind why using interferometer is to get really good resolution on small scales. But for cosmology, we're not necessarily that interested in the really small scales. And in fact, the interferometer becomes a bit of a challenge. If we were to use as an interferometer, we're not necessarily sensitive to cosmological scales. And this is because the field of view that you can record with an interferometer is limited by the how small these baselines become. In other words, how tightly packed all of these dishes are. And for the SKA and for MeerKAT, these dishes aren't sufficiently tightly packed enough to be sensitive to things like the BAO scale, which of course what we're interested in. So in order to get around this, we take this nicely designed interferometer, and instead we don't use it as an interferometer at all. We just use it as a collection of individual scanning autocorrelation dishes. So this means we now have no baseline limitations. Literally the sky's the limit in terms of how large we can make these surveys. And we also get the added benefit that now one night's observation becomes however many dishes of night's observations we have. So for like MeerKAT, one night's observation now becomes 64 nights of observation. So you can see how this is a very nice, efficient, quick way of conducting larger amounts of observations. The sort of one drawback to this approach is that now your resolution is not that great, because now your largest baseline, which determines how what small scales you can probe, is now just your dish diameter, which would be about 15 meters for the SK and MeerKAT case. So that's why we have these quite blurry looking maps now. So we're not that sensitive to the small scales. But if you're doing large scale structure, hopefully this isn't too much of a problem. Right, so these are the observations that we have now that we're working with, and this is what we've made a detection with. So yeah, it's what we call pilot survey data. So it's only about 10.5 hours of data that we have just from 6 nights of observations. So just calibrating this data using this single dish technique that I just explained, just sort of calibrating maps from this set of data was a challenge in its own right. This is actually the focus of this paper, which we published last year, some work led by Jingying Wang. So what you're seeing here is the data that we have. So it's really just showing the foreground sky here. But it's about 200 square degrees of sky that we can already get just from this small amount of data. So you can see how if we start to record more data with more hours of observation, which we intend to do, you can see how this sky area that you're going to capture can easily be scaled up. So that's what we intend to do over the next couple of years. So for this data, we're technically sensitive to all of these redshift ranges here, all these frequency ranges, but we actually find we're sort of quite limited by RFI, which radio frequency interference. This is still something we're trying to understand how we can best deal with this. But for the minute, what we're doing is adopting quite an aggressive approach and cutting or flagging a lot of the channels out. So it's only this small thin sliver of frequency channels that we're using here, just about 200 frequency channels in the most RFI free range that we can find. We find this is necessary to achieve the cross-correlation detection. So this will be a challenge for future observations, trying to improve this. Hopefully going to UHF band might be a way of doing this, where at those lower frequencies, RFI is less of a problem. So another challenge for this kind of observation is, of course, foregrounds that you have. This foregrounds is kind of something that's almost synonymous with intensity mapping. It's always seen as a problem. And it comes from the idea that this novel observation technique that you have, where you just integrate all radiation that's you receive to your telescope, you're not just going to receive cosmological H1 when you do this. You're obviously going to capture things like RFI, as I just explained, but also any astrophysical processes that are emitting signal in the same frequency ranges that you're observing. So that would also include what we call foregrounds. These come from astrophysical processes like galactic synchrotron, free emissions. These are both things that come from within our own galaxy. Also things like point sources, extragalactic point sources. And as you can see from the simulation example, all of these foregrounds dominate the cosmological signal by many orders of magnitude. So we have to remove them to have a chance of observing this. So the way we do this, as you'll also notice from this plot, which we know to be quite true, is that the foregrounds have a continuum spectra, so they're very smooth through frequency, unlike the cosmological H1. So we can utilize this in a foreground cleaning. So what we do is we do a blind component separation technique based on principal component analysis. So we take the frequency covariance for the data. Because the foregrounds are very correlated in frequency, the first few principal components of this data should contain the correlated and very dominant foregrounds. So you remove those dominant principal components, and it should leave behind the cosmological H1. And that's exactly what we do in our real data. In the real data, though, we find that these spectra, they're not quite as smooth as we'd hope, and that's largely down to calibration issues, which we'll obviously try and hope to improve. And there's also probably some other residual systematics in the data as well, which will also be adding in extra components. So we have to remove about 30 principal components from our data to do this foreground clean to a sufficient level to get a detection. And we reconstruct for any signal loss that comes from that with a transfer function, which I'll have to refer to the paper for details of that. Okay, so this is the main results that we get. So yeah, this is a cross-correlation detection. So I show the two footprints for both data sets here. So because we knew this pilot survey data probably would be quite high in noise and likely have some systematic dominant components, we targeted an area with a galaxy survey so that we could do a cross-correlation. And then by doing that, you cut through a lot of these systematics and noise to achieve your detection. So we cross-correlate with the WiggleZ 11-hour field, shown here in green. MeerKAT pilot survey is shown in red. And then on the right here is the cross-correlation power spectrum from these two fields. So if the idea is if there was no cosmological H1 at all in our intensity maps that we observe with MeerKAT, then there would be no cross-correlation signal between these two data sets. You'd get something that was just consistent with zero. So these power spectrum, any hollow points here are showing negative power. So if you had zero correlation, you'd get a lot more negative power points than across all scales. But clearly that's not the case, especially at high K, where we're most sensitive to. So these are, sorry, at low K, which is large scales, we're most sensitive to these scales. We get a very good cross-correlation detection. It works out as about 7.7 sigma cross-correlation detection. So this is really a first detection of its kind. What I mean by that, there's been intensity mapping detections before, but this is the first one that's been done with a multi-dish array using this single dish mode of observation. So it's a really important milestone for something like SKA, because the SKA will ultimately be relying on this single dish mode of observations to achieve its large-scale structure cosmology objectives. So it really needed to pass this test. So it's a great first step in that direction. Okay, so I mean, even though this is just pilot survey data at this stage, just a small amount of observation, we're not super sensitive to cosmological parameters yet, but we're already sensitive to some astrophysical parameters. So one of these is the H1 abundance. So in other words, the omega H1. So the reason we're sensitive to this, if there's more H1, it should boost the amplitude of your power spectrum. So just by constraining the amplitude of the power spectrum, you're sensitive to this parameter, along with some other quantities as well. So the H1 bias will also affect this, and also the cross-correlation coefficient, which just accounts for the stochastic nature between the H1 field and your galaxies. So this is the full quantity that you're sensitive to when you constrain the amplitude. And this is the final result we get. But if you make some assumptions about BH1 and the cross-correlation coefficient, you can just reduce this to a measurement on omega H1, which we show here in the context of some other results in the literature. And these are all done at different redshifts. And you can already see from our result in the blue, it's already delivering quite a competitive result relative to other literature results. So this should only get better, and tensor mapping will be a very good way of constraining this parameter at higher redshifts. One thing to point out, though, as I'm showing here on the plot on the right, is this result is scale dependent, but that's largely probably driven by the fact that the H1 bias and cross-correlation coefficient we know will be scale dependent. Omega H1 shouldn't be, so it's probably these two that deliver the scale dependence that we see here. So we test this just by doing various scale cuts of the data, and but it's showing a nice trend with some other data from the GBT results as well. Okay, so just to quickly show some reasons to be excited about the future, we have all these observations coming up. We're doing things in higher redshift and UHF band, and hopefully going to go to larger and larger sky sizes, and we'll hopefully be able to try and achieve all of these science goals. So yeah, the main result I show here again on the right. This was a detection in cross-correlation about 7.7 sigma, and yeah, we're very excited about all the sort of future data that's on its way. It's arriving very fast. There's lots more science to be done, so please stay tuned for all of that. And yeah, thank you very much for your time. Cheers.